Hi, let's start today's content. Today's content is the outline of the bioengineering. Okay, what is bioengineering? And research example and some of the medical application system introduction and history and relating societies introduction. Okay. Hi, let's start from this. As I said, this course is designed firstly for the bioengineering course student. So therefore, I started with this. What is mechanical engineering? Mechanical engineering is basic technology of the four major dynamics. Four major dynamics I have explained last week. The material dynamics, fluid dynamics, and the thermal dynamics, heat dynamics, and the mechanical dynamics. And based on these dynamics means not static, because the machines systems is work. It has its physical body, and the physical body makes some movement. Not only the static movement, but also the dynamic movement. Dynamic movement means accelerate, decelerate, and so on. More complex movement, not the constant speed, but many various kind of movement is generated. So for example, the transport machine and the production machine, processing machine, control instrument, and factory automation, and so on. So therefore, not only the physical body, but also to control it, the electronics, computer science, information science, material physics, chemical processes, and so on is necessary. And not only the engineering field, but also some elemental surrounding technologies. So therefore, we will do the mechanical machine, environmental machine, and the mechatronic systems. Then, what is the difference? The usual engineering and bioengineering, the living things, biological body. Why it is difficult to treat the biological body? First item is it's too complex, very complex material, complex structure, complex composition, complex complicated dynamical features, and so on. So and also the many unknown parts are remaining. So therefore, it is difficult to simulate, analyze, modeling, analyzing, and simulating. Okay. And the second part is a living creature. So therefore, if it is even in the surface skins, if it is removed from it, it will become, these features become changed quickly, because it become die and of course dried. The condition will become different. So therefore, it is difficult to treat in the original appearance, original conditions. To make a model, 例えばスキンサーフェスモデル、なんかハンドでも何でもいいんだけど、このスキンのサーフェススキンとかあって、それのなんかじゃあ we want to know the dynamic feature of skin, for example, dynamic feature. Dynamic feature means some mechanical feature of surface this material. For example, we want to know for example なんか elastics だから last week I have said elastics and viscosity to calculate the spring constant of this material and the viscous effect of this material we want to know to make a model. But if it is to measure this spring constant and viscosity, one simple way is material is here and the pulling it, make a force and pull it, and then this deformation, we will observe this deformation, and then we can estimate these materials, the feature like spring constant and viscosity, for example. But this skin is cut from this arm. The feature, this material's feature will become changed quickly because it is dyed and also dried and so on. The mechanical feature will become different when cut out the dye soon. Yeah? So therefore, it is very difficult to measure even only these kind of mechanical features. And thirdly, the living creature has some activeness, the positive, active movement by itself. Not only passive, but also some active movement can give some stimuli. It has reactions, reflection. For example, some nerve system has some reflection effect. So for example, if it is the knocked of this knee, it has changed like this. So therefore, some active movement is shown like this. So therefore, it is completely different. But the bioengineering is very, very important because the one is deeply understand of the living creatures. This is molecular from molecular level, the cellular level, and individualモレキュラーレベル、セルラーレベル、それからオーガニズムレベル、ね、オーガニズムレベル、それからインディビジュアルレベルか。インディビジュアルレベル。So therefore the several levels, the living body's structure, function, understanding from the viewpoint of engineering viewpoint, we can understand deeper about the living creatures. So the understanding make contribution to the medicine biology itself, the medical understanding itself, and also the correct understanding makes the good medical diagnosis, medical treatment, and the health and good sanitations. So therefore, it is also contributed to the health maintenance and the body strength increasing. So that it is a social contribution. It is lead to the social contributions, societies. That is the second point. And thirdly is the engineering viewpoint. The living creatures is after the long term, the generations, so the evolutions. So therefore, it is designed optimal and ideal. It seems to design optimal and ideal. So therefore, this kind of structure, features, understandings can be applied to the engineering research and technological development. It is also there. It is similarly shown in the ここに書いてあるんだけど、it is also shown in the same things. The fundamental research, basic research, know itself, the understand of the living creature itself, and the medical applications. The engineering aspect, if it is understood in the engineering aspect, it can be contributed in the medical welfare technologies. And then it is also the fed back to the engineering itself, its applications, the optimal design or optimal manufacturing and so on. で、ここに戻ると。So therefore the bioengineering area is, in many ways, it is said in many ways. The biological engineering is near to the biological viewpoint. Medical engineering is medical, so near to the medicines. Biomedical engineering, BME is commonly said, and medical electronics is also commonly said. The medical electronics meaning the living creatures signal processing is the main interests. Medical and biological engineering is also said. But we think when based on the mechanical engineering, so the biomechanical engineering is bioengineering and mechanical engineering is combined. It is said in this field, one is bionics. Bionics is aiming for the technological application applied to the technologies, including the information technologies. Maybe you may have heard about cybernetics, word cybernetics. Cybernetics means the sum of the artificial intelligence. So therefore, not only the body, but also the signal processing or the data processing is also included in the bionics. Biomechanics is mainly for the mechanisms and dynamics. Looks like this. And it is also said Biomechatronics, Biorobotics. It is used like the mechatronics is only the mechanics and electronics, but adding the biological viewpoint. And the biorobotics is also similar. The target is a robot, but also adding the biological aspect viewpoint. This is only naming. Not so much important, not so much meaning on this. The classification is a little bit difficult, but the one classification looks like this. One is the living creatures element understanding, and the second is the function understanding, and the third is the total body, individual maintenance. So the element understanding is also the similar as several classes. The material layer, tissue layer, organ layer, and the individuals. The individual looks like this. The second layer, second part. The individual's entire individual no physical mechanism is understood. And then based on these understandings, it will be applied to some human movement or human works and so on. So therefore the third part is becoming the rehabilitation engineering, health and welfare science, and sports sciences. Next, I will explain introduce some examples. The first, the basic research. The basic research means the living creature itself, understanding living creatures itself. It is several levels. the molecular levels and cellular levels, tissue levels, organ levels, individual levels, and so on. So here it is said the component material, construction, structure, and configuration, its dynamical behavior is such. Biological molecule, cell, tissue, organ 書いてあるんですけど、の property, deformation, and strength, and so on is observed, detected, and storing the data. This is fundamental. So dynamic behavior too, as I said here, the dynamics is very important to make the model, some models. So therefore the dynamic features detection and observation and detection is one of the fundamentals. Observe, detect. The secondly is inside outside body's flow. The inside flow is blood circulation or the respiratory apparatus. It means breathing using the lung, and gastrointestinal substances. It is consumption of the energy generation, and urine and the joint fluid is here. And so therefore this is the inside body's flow. All of them is the inside body's flow. But also the outside body's flow is one important, because fish swimming or the birds and insects flying is very important to know, to understand. It will be applied to the designing the wings of the aircraft, for example. This. And thirdly is the metabolism, exchange. Last week I said metabolism is based on the material exchanges. So not only material, but also the heat is also the inside-outside transfer, and oxygen is also outside-inside transfer. So the thermal property and the heat movement, heat transfer through the skins, and oxygen material exchanges in the peripherals is also. This is mainly the thermal dynamics. And this is also the many levels and many parts is the focused, the organ level, the parts level, tissue level, and so on. So therefore, for example, the joint dynamics characteristics measurement, and the spinal cord movement, mechanism and movement, and the total postures and the gait motion, walking motion analysis, and the impact against body reaction against impact. This is also important for the safety of the vehicle drivers. So which kind of impact can be resisted by human body is one important issue. Okay? Vehicles. And also presently it is spread to the robot, because human-robot interaction is already realized. So therefore the impact by not only vehicle accident impact, but also the robot accidental contact with the robot is also the one big issue about this. And heart, eyeball stress analysis, lung function analysis, because breathing constantly, and auditory organ function analysis, and sound propagation analysis, and so on. So if you watch this like this, you can see the first part is the dynamics. So therefore it is related to the material mechanics. And this is a fluid dynamics, hydrodynamics. And then this is third part is thermal dynamics, heat engineering. And fourth part is the mechanical dynamics, the material level and the fluid level, thermal level, and the mechanical level. It is related to the dynamics you can understand. ですね。それはファンダメンタルリサーチワーク。Fundamental element understanding, fundamental to individual understanding is necessary to modeling. As I said, こういうデータ based on these data, we can じゃあデータから analyze, analysis だよね、analysis, and then the modeling.Make model and then simulate. ですね。Gathering information and then make this data is analyzed to make a model. And when we can establish a model by using it, we can simulate these dynamics or some future movement.はい、次はメディカルアプリケーションということで、メディカルアプリケーションなんですけど、何ですか、ダイアグノシスエクイプメント、メジャーメントインストゥルメントとかですね、とか、あるいはメディカルトリートメントのディベロップメントをやったり、あとはアーティシャルマテリアルとかアーティシャルオルガンのデザイン&ディベロップメント。Artificial skin, artificial bone, artificial heart, artificial cardiac valves, the blood vessels, and so on. And the processes, artificial limbs, the artificial hand, artificial leg, and so on. And also the wheelchair or some gait training equipment is also including here. And also the sports equipment to make the physical body stronger or the enhancement of the training. This methodology and the equipment we can develop. This is a medical applications. And thirdly is technological engineering applications. As I said, biomimetics. Mimetics is from biological body we can learn a lot, and then what we learned is applied to some engineering something is the biomimetics. Then, for example, the movement structure is imitated. And then the new functions is created in robot or some the materials or structures, new robot, new materials, and so on. One example is honeycomb structure. You know honeycomb? Honey, bee ね、bee. B, これです B です。B leading part is looks like this. So this is very B high. This is hint from this B high, and lightweight material is designed because honeycomb structure is very strong for this part. ね、だからカーボンボックスじゃないカードボックス when we develop the カードボックス、これってなんか見ようか。じゃあバイオロジカルこれ見ますか。 EBC2
This almost looks man-made, manufactured, and
Yeah.
it doesn't look like
Yeah.
something from the natural world. The precision, the fine straight lines that they've created
Right.
is extraordinary.
Right. It's an engineering wonder for sure.
Look at this, it's perfect. Hexagons here.
It is amazing. And the hexagon is a very strong structure.
The bees have made an identical pattern to the columns on the Giant's Causeway. Each cell is exactly like the others, 6 walls meeting precisely at 120 degrees. And every honeybee, everywhere in the world, knows how to build these shapes. It's as if the hexagon is built into the bee's DNA.
You can see the bees going down inside the cell. It's almost exactly the same size as their bodies.
Right.
Are they using their body like a ruler in some sense to do the job?
I would say that's an accurate description. I know different races have a smaller body and the cell size in their cone is smaller.
And each of the hexagons, how do they actually make a hexagon rather than some irregular shape?
They've just done it for thousands and thousands of years. They were born to do it. They just instinctively know that this is the shape of their home.
But there's more to the bee's behaviour than raw instinct. There's another reason why they build in hexagons. And to reveal that reason, we need to turn to the universal language of all nature, mathematics. The bee's primary need is to store as much honey as they can while using as little precious wax as possible.
The bee's honeycomb is an amazing piece of engineering, but why have they evolved to produce this hexagonal pattern? Well, actually, they don't have too many choices. If you try to put pentagons together, for example, they just don't fit together nicely, or circles leave lots of little gaps. If they want to produce a network of regular shapes which fit together neatly, then you've really only got 3 options. You can do equilateral triangles, or you could do squares, or you can do the bee's hexagons. But why of those 3 does the bee choose the hexagons? Well, it turns out that the triangles actually use much more wax than any of the other shapes. Squares are a little better, but it's the hexagons which use the least amount of wax.
It's a solution.
It's a little amount of wax, but the strong structure can be achieved by using this. So therefore, it is practically applied cell pack like this.
For more than 20 years, Honeycomb Cell Pack has manufactured environmentally friendly packaging for the fixing and shock absorption of products during transport. Our packaging is paper-based. This means natural products, new paper, craft liner from wood and or recycled paper, and water-based glue. Our packaging is therefore 100% recyclable and biodegradable. The core in our honeycomb packaging has a unique cell structure, hence the name honeycomb. This natural construction of cell-shaped air-filled spaces makes the packaging very strong and very light at the same time. Often, our packaging replaces EPS, expanded polystyrene, which is an oil-based product that does not have the same environmentally friendly properties as paper-based packaging. We supply a wide range of European customers who use the packaging for shock absorption and fixing of all kinds of different products.
っていうようにパッケージングとかも it is practically used this kind of thinking. One example. これですね。Second example is vortex generator. Vortex generator is old weather. From the old weather, some tiny protrusion is appeared at the end. So therefore, if I show some videos, it shows これなんかthat is some some wing ね、wing だから wing で claw is here ね。After some wings, the flowing like this, and after some wings, in some cases, it makes the winding areas, the tornadoes like this. It makes some sound noises, and also it makes reduce the bad impact for this. After this wing shape, it should be smooth flow is more better. Smoother flow is better. But this screwing winding area is not good for the efficiency. So therefore, if you take some, put in some small chips is given here. Small chips is shown here. Like it makes more smoother flows. だからこうなってるところにちょっとこうなってるウィングのところに only smooth is tiny chip is attached here, so therefore it makes more smoother flows. Without this, it makes some screwing noises. So therefore, you can estimate what it is.これ何だ？これ何でしょう？これはこれトレインのパンタグラフのところにこうエレクトリックのコレクターがあるでしょ。ここにpushing it and the electrical power is distributed from here. で、パンタグラフみたいなやつ。で、this part has some here, and this train is go high speed. So therefore, it makes the small chips is given here. It makes a very very bad noises. So therefore, put some chips on here and makes the flow smoother. So reduce the noise. でちょっとボルテックスジェネレーターのところを見てみますが、これは多分エアプレインだかなんだか。
This is a vortex generator. People often loosely understand what they are, think they understand what they are, or sometimes just don't know at all. Today I'm going to explain how they work and debunk any myths or misconceptions you may have had about them. To start with, I seem to get a lot of hate on some of my videos because people seem to think I don't know what I'm talking about. So a brief history. I am a university medalist aerospace engineer who majored in race car aerodynamics. I've worked in the racing and aerospace industries and am currently a researcher in the field of vortex generation and flow separation control. I have published papers in top-ranking academic journals regarding this stuff, so trust me, I know what I'm talking about. So let's start with why we need vortex generators and work our way back to how they work from there. Let's say you have a flow traveling along a flat plane, like this. At any point on that surface, the flow has to be stationary. It's a basic fluid law. So what you end up with is a free stream flow velocity, a stationary flow velocity, and some sort of profile going in between there and there. So the flow here is slower than there. This is known as a boundary layer, and is where a bunch of turbulent mixing occurs, and it's got several different zones. That's not important. Now, if you transfer this concept to a curved surface like this, you can imagine that this flow will try and stay attached to this curve the whole way down. So you'll end up with a flow path like that. This leads to our two main regions of flow. You can characterize most flows by separated or attached. This is an attached flow, as it follows the surface. A separated flow will
move off from the surface and go over here. Why does this occur? It is because you end up with something known as an inverse pressure gradient as you travel around the surface. This flow wants to continue going straight, this surface wants to pull it down. So you end up with a suction, inverse pressure. This will cause an eventual reversal of the boundary layer, which will then cause it to spiral around like that in what's known as a separation bubble, while the flow kicks over the top. This is largely due to the low energy level of the boundary layer, with respect to the high energy level up here, being able to pull this off the surface and keep going. This will only occur at a certain critical inverse pressure gradient, so it's defined by angles, things like that. Now, why is flow separation bad? Let's consider a basic example. In layman's terms, imagining a basic example like an inverted car wing is quite simple. You can think of it as the flow comes in here, and then we want to deflect the flow up here and end up with it somewhere over there. Now this means we want to keep this flow on here so that it shoots up there, and this flow up here. This flow here is obviously going to stay attached, because it doesn't have an inverse pressure gradient as it's pushing into the shape. This flow down here, though, does have an inverse pressure gradient, which means that depending on the wing profile, you may end up with the flow shooting up over here, which results in a much less efficient wing. And here's where it comes on what vortex generators actually do. Vortex generators allow you to control the point of separation better by delaying it further. This means that with more intense curves in your geometry, you can keep that flow attached for longer and thus get better efficiency for your given profile, or make the flow do what you want it to do.
You understand? You understand? これと同じことなんだけど、Why the airplane can fly? You know? Why airplane can fly? こうなんかね、airflow is here. Airflow the small in a small speed. It works in around this wing. Around this wing. ね? Slower speed, it flows around this wing correctly. でこの around this wings, following this shape. And the pressure force is lower pressure, higher pressure force, but this high pressure force is smaller. So therefore, totally this wing can flowing up. It's the principle of the flying. Okay, so this wing to go these wings, but this flowing force is appeared because the higher pressure force and the lower pressure force, totally this wing is flowing. This is a working. This is a work principle. But for this higher speed is given here. The flow is released from not following this shape, but flow is released, separated from this shape. So this vacant space, the rewinding air is generated here. So it makes a separation of the flow. It's a very bad condition because this is very complicated pressure is given here. So therefore this flowing pressure is flowing force become reduced. Okay? So therefore this winding air should be reduced. So therefore vortex generator, its small chip is given here and makes the air flow smoother. っていうのが原因なんだけど、っていうのがここにあるで、もう一つどっか例えばこれも。So
I recently had access to a 3D printer, and it's really cool how many 3D parts and models are out there free for you to print into real life. I am an instrument-rated commercial pilot, currently training to be a flight instructor, and so I've come across vortex generators before as used on aircraft wings. I logged a dozen hours in a paper Super Cub with VGs installed on its wings. But what do these things actually do? Let's take a minute to see how moving air reacts with a solid object. Because air has friction or viscosity, it can act a little bit sticky. Not nearly as much as honey or oil, but it's there. And if you have a free stream of air moving along a solid surface, the air next to that surface gets slowed down by it, and that friction propagates upward. This area of slowed down air is known as the boundary layer, and is why you can never quite blow all the dust off of things. As air flows around a curved surface, it would like to follow that surface all the way around. If air did not have any friction, it would flow around this ball symmetrically. High pressure at the front and back, low pressure at the top and bottom. And there would be no drag because the pressures are symmetrical and there is no friction. However, what you actually get in real life is a wake. This right here is particularly interesting because the air is going from an area of low pressure to an area of greater pressure. And that's kind of weird because things always want to go from a higher pressure to a lower pressure. But the air has enough speed and momentum to push through it. With no friction, the air would conserve all of its energy from accelerating around the ball, and have just enough to leave the other side at the same speed that it started at. But since it has been slowed down by friction, the boundary layer doesn't have enough energy to push through. It slows down to a halt and then actually starts to go the other way at the surface. And right there, that is when the airflow separates, and that area of reversed flow is called a separation bubble, where air is recirculating and it has a lower pressure. And the difference in pressure between the high ram air pressure in front and the low pressure separation bubble in back causes a force known as pressure drag. Another way to look at it is that the air has mass, it has weight and momentum, and at the front of the object there's a point called the stagnation point, where the air is compressed and the velocity is brought to zero. It's like we are constantly grabbing air and pushing it with us. Similarly, the wake in the back is a low pressure separation bubble where we are grabbing a bunch of air and pulling it with us. We are giving it some of our energy and then letting it go, and then grabbing some more. I noticed that the raindrops on my car's rear windshield wouldn't get blown off when I would go down the freeway, indicating that the air has separated and was not attached. So I thought it'd be a cool idea to try and 3D print some vortex generators and then put them on my car's rear windshield and see if they would help delay airflow separation. Here is my test. As you can see, without the VGs, the telltales are swirling all over the place from the circulating currents in the separation bubble behind my windshield. With the VGs installed above the middle section of the window, we see a huge improvement. This theoretically reduces pressure drag, however it does increase lift at the rear wheels, which reduces traction. But how do these vortex generators work?
という話でした。OK。まあ、almost understanding about this. これが second example ね。And third example is athletic swimming wear. Swimming wear. For example, the swimming wear is very important for the swimmers, especially for the Olympic record swimmers. So therefore, the reference the shark's skin or the penguin or Alcido's the water prevention quality like this. This is a lotus leaf cases, and also shark skin looks like this, or the penguin's skin. Penguin's skin looks like this. どっかにここにシャープのやつがあったよな。Must of shark skin とか見ますかじゃあ。Must of shark skin.
I think sharks are really fascinating animals. They are a kind of maximum in the evolution system. So they are almost perfect animals. And in this respect, we can learn a lot from sharks. Shark skin is not smooth as one would expect, but it's very rough, and this roughness is making them faster in the water. Why this roughness is improving swimming? There is a reason, and the reason can be explained in mathematical terms. Okay, when we have a shark in the water, in this region around the shark, there is another dynamics related to what we call the water viscosity. So the water viscosity is responsible of resistance of the water to the swimming. This occurs like when you take cards and you throw these cards in this way. So the fluid, each card is a kind of layer of fluid. slipping one over the other. And this is the action of viscosity. This action is creating some vortices on the surface of the shark. And these vortices are dissipating. Now, if the surface is not flat but is rough, like we have on shark skin, this roughness is breaking these vortices, is reducing the occurrence of these vortices thanks to water trapped in these valleys of the riblets. The roughness of the shark skin, the presence of these riblets, makes the shark faster. In the Olympic Games of 2004, a couple of companies tried to reproduce this effect on the swimsuits of Olympic swimmers. And I was working with one of those companies, and we reproduced mathematically the effect in order to quantify the real advantage and try to identify an optimal shape and an optimal sizing of these riblets. We found an advantage, a reduction of drag at around 14%. After Olympic Games of 2008, these wingsuits were banned because they are this kind of technological help is supposed to be, or is considered to be, a technological doping. One of the most important things of mathematics is that you can do experience in one field, like sharp things, and then use this experience in a completely different fields, like motorcycles or blood dynamics. We can use...
まあいいや、というふうに based on the shark skin, different to the shark skin, the shark's skin, the swimmer's suit is designed newly. というのがこれ、example. 他にも other example is the optimal design technique generation とかいうものがあるし、and also the system analysis is also there. The some modeling and simulation. はい、this is example ね。次は Next is the equipment example, but you may know the CT scan and MRI and looks like this. The presently not only the cross-section diagnosis, but also the presently the blood flow is also simulated, observed by using the CT scan or MRI. Okay. And in this case, from this captured image, the image processing is very, very important in this field. Medical image processing is very, very important. So therefore, like Prof. Kamata's laboratory doing this kind of work. And another diagnostic system is endoscope for inspection in the gastron, and also the ultrasonic diagnosis system, like this, scanners, and also the capsule endoscope is also presently commercialized. And more welfare apparatuses. The electrical chair is also one example. This is a modular type electric chair, and also this is a stair climbing wheelchairs, and this is a standing up type. Is developed more than 20 years ago. And artificial processes like hand and legs and knees and so on. And also the socket is also very important. This is attachment for the patient's body and the artificial limbs. Socket is also very important because this is depending on the individual users. So therefore the shape is very important. So for each customers, attached to each customer's legs, this socket design and the measuring and the designing is also very important. Presently, the 3D printer is used to design and manufacturing these parts. And also the surgical robot. Surgical robot system is already practically used, like this is Da Vinci system. So the coronary surgery, for example, This is a surgeon. The medical doctor is the physician is operating the two joysticks, and these 3 arms is moved, and then the surgical operation is done by using this kind of the end chips. From this part is a history, small history of the medical bioengineering. これなんだ。Pythagoras. This Pythagoras is the say the brain is the most important part of the physical body, the human body. And then Hippocrates, like this. Hippocrates is also the very important because he is called father of medicine. Why it is? Because the Hippocrates defined oath of Hippocrates. Oath of Hippocrates indicating the morality and objectivity of the medical thoughtness, medical consciousness. Oath, the saying, it is up to now that it is used for the graduation of the nursing school or graduation of the doctoral school. In the graduation ceremony, this oath of Hippocrates is said together. For example, this video you can see these videos.
I solemnly pledge to consecrate my life to the service of humanity. I will give my teachers the respect and gratitude that is their due.
I will practice my profession with conscience and dignity.
The health of my patient will be my first consideration.
I will respect the secrets that are confided in me, even after the patient has died. I will maintain by all the means in my power
The honor and the noble traditions of the medical profession. My colleagues will be my sisters and my brothers.
I will not permit considerations of age, disease, or disability.
Creed, ethnic origin, gender, nationality, social standing, or any other factor
To intervene between my duty
and my patient.
I will maintain the utmost respect for human life.
I make these promises solemnly,
I make these promises solemnly,
freely,
freely,
upon my honor.
is also the certain graduation ceremony like this. So the Hippocrates is very important because they are challenging to the superstitions and ignorance, and also the declaration of some speculations and hypotheses. So therefore the experience and observes and the fact-based thinking he started. But the for temperament he said that this is a little bit different from viewpoint of the common understandings, but he proposed this assumptions. Hippocrates is one important person in medical histories. And also you understand that Leonardo da Vinci is not only the painter, scientist, but some of them is they are very interested about the human bodies. So therefore he made many sketches like this, and he found the blood vessels, some calcium is deposing inside of the blood vessels, he found. And also based on the bird and bat observations, he proposing some wings like this, and aircraft and propellers like this. And Galileo Galilei is mainly famous about the astronomy, but also the medicine, mathematics, physics he has done. And so therefore the motion analysis of for example, not only the pendulum movement, like this pendulum movement, the constant time, but also this scaling factor is also thinking, analogy. Analogy ってスケーリングって分かるよね。Maybe you know the scaling. small bone とかで、もしもこれが only the similar size, the scaling, the bigger, ストレス、これ F ストレスね。このストレス&ディフォーメーションなんかディフォーメーションなんかデルタ X かね、デルタ X でこれスケーリングこのストレンスボーンのストレンスって decided which part the bone strength is decided. Maybe the cross-section area でしょ cross-section area. Maybe the bone stress is decided by cross-section area. ね、これクロスセクションってサイズの2ディメンショナルだよね。サイズの2ディメンショナルだよね。ね。だけどこの例えばボーンのトータルウェイトって3ディメンショナルだよね。3ディメンショナル。ね。でだからスケーリング、if the scaling is twice scaling。ね。twice scaling makes the twice scaling。だから、area, cross section area is 2 by 2の4 times。ね。But the weight, total weight is 2 by 2 by 2 の8 times。ね。8 times means this system is some なんていうかな、resistance っていうか、feasibility というか resistance っていうか、but the strength become force, but the weight become 8 times. It means the strength become half でしょ。このなんかさ、weight performance ratio って考える。weight performance ratio, this is まあ1 but this is the strength is become force, but become 4 times, but the weight become 8 times. So therefore the weight strength ratio become half. でしょ It's no good. So the scaling growing by the same scaling is no good. で it can be estimated. でしょ So these kind of things, the Galileo Galilei is estimated. This is not only analogical generation, analogical growth is no good enough. でしょ So therefore the baby's body and the ordinary adult body is become different なんていうかな、スケーリングとか different balance でしょ。ベイビーはもっとヘッドが大きい、ラージヘッド。The adult はスモールヘッド。ベイビーはショートレッグス。 short legs. あとアダルトは longer legs. Not the same scales. Not analogically growth. Not analogically growth. Deforming while growing. This is said by the Galileo Galilei. もう5分前ですね。で、so therefore this is also a very important point. あとはハーベイという人はこのブラッドサーキュレーションを発見した。ブラッドサーキュレーション、ハーベイ、found. And Descartes is a physician. あ、違った。フィジシャンじゃねえ。フィロソフィーの人で。デカルトはフィロソフィーで、but the takes to the all っていうのはなんか、saying about the humans is one physiology's textbook he published とか、あとはボレンリっていうのは、まあ、特にエアーについてボイルシャルルっていうボイルシャルルズローっていう you may know about the temperature pressure relationship, but he also found the air is very important for the living. Because cat in a vacuum chamber, cat become dead. He experienced. And also Hook is founding this cell by using this microscope. But also the Hook also found the Hooke's law, spring law, of course. So therefore, not only the physics, but also, in recent years, Young っていうと、in the mechanical engineering, Young's module to Young's coefficients is very important. This is a elastic coefficients なんだけど、he is also searching on this eyes, retina of the eyes, and also the three color detection system is he found とか。ハーゲン・ポワズイユのポワズイユっていうのはフルイドダイナミクスの人なんだけど He is a fluid dynamics specialist, but he found it by observing the dogs, the blood circulation flowing とかですね。あとホルムヘルツっていうのは、イヤーとかアイとかイヤーのリサーチワーク he has. But Holm Health is very famous about the energy conservation laws. Of course. ということで、バイオエンジニアとかバイオジャスメン、ジャパニーズ・ソサイティ・オブ・メカニカル・エンジニアのバイオエンジニアリング・ディビジョンとか、これはジャパニーズ・ソサイティなんだけど、アスメっていうのはアメリカン・ソサイティ・オブ・メカニカル・エンジニアのバイオエンジニアリング・ディビジョンとか、IEEE のメディスン・バイオロジー・ソサイティとか、You should access if you have some time。ね。ということで、all of them is explained. OK? ということで、これはリファレンスね。next week、今週tomorrow, from tomorrow, this event, exhibition will be held. And next week is 福岡。これはこれで。あと、next month, November に Welfare Equipment Technology Fair あります。